Hello. So I'll start the lecture as soon as somebody can let me know in the chat that they can hear me and they can see the video stream. So today we're going to discuss about object localization, object detection, and faster RCNN, and also the great, thank you, and also the models that were introduced before faster RCNN and are sitting at the basis of this state-of-the-art object detector. So we're dealing with convolutional neural networks. So just a brief recall about a convolution. So the convolution is an operation that is based on applying a set of filters on top of an input image, and depending on the location of the convolution in the neural network, it can extract various features, from low-level features that activate on patterns such as edges, corners, and so on, to high-level features that activate on object parts. So yeah, intuitively, since these models are able to recognize object parts, they are also useful for localizing and detecting objects in images. So today we're going to see how these models can be adapted for this task. And another layer in this model is the pooling layer, which is typically done using MaxPooling, and this keeps the maximum activations from the activation maps that are produced from a previous convolutional layer. So this also helps to reduce to make the method equivariant with respect to the location of objects. So yeah, localizing objects is possible, but we have to see how we can modify the framework in order to do this. And yeah, convolutional neural networks evolved from the LeNet architecture introduced in 1998 for recognizing handwritten digits from the MNIST dataset, to AlexNet in 2012, which was the first breakthrough on recognizing objects in natural images. And since then we have deeper and deeper architectures until ResNet was introduced in 2015. And with this model, which is based on the residual connections, we can train now networks with even 1000 layers. Okay, so our plan for today is to see how we can use these models for localization and detection. And these are two independent tasks. So detection, here we have some results where we have objects with bounding boxes around them. So this is the detection task, and the localization task is just localizing a single instance of an object. Okay, so we have the classification task, which is we are given an image with an object and we have to label it. So this task is fairly simple and straightforward for convolutional neural networks. Then we have the classification and localization task. So now we have an image of an object, but we don't know the exact location of this object in the image. So besides providing a class label, we also have to localize the object inside the image. And these two tasks refer to images with a single object. So if we want to go to multiple objects, then we have tasks such as object detection. So here we have different instances of various object classes, and we have to identify the classes as well as the locations of the objects in images. And the location is typically indicated through a bounding box that is tightly fit on the object. And we also have a more fine-grained task, which is called instance segmentation or semantic segmentation, in which the image is segmented. So essentially this is a pixel level classification task. So each pixel in the image is associated with a class label. And from this information we can obtain these semantic segments. So we have here a segment of a dog, some two segments of cats, and so on. So we'll start our discussion with the first task that involves finding the location of objects, which is the localization task. And in the second part of the lecture, we will discuss about object detection. Okay, so if we want to do classification, we know that for the input image, we have to predict some class label. So we have to define a function that maps this input image to the specific label. Whereas for the localization task, we have the input image and we have to produce 4 outputs that give us the location of the bounding box for this image. So intuitively, we have a function that produces four values instead of a single value. So in the end, actually, we want to localize objects and also to classify them. So we have to do this to solve these tasks jointly. So this is called classification and localization of objects. And this task is typically also proposed in the ImageNet challenges. So these VGG and ResNet models were also tested on the classification task, but also on the ImageNet localization task. So this is done with the same number of classes, 1000 classes from ImageNet. These are the exact same classes as for the classification task. And here for each image we have to indicate the correct class and the bounding box of the object. So there are around 800 or 1000 training images per class, and the goal of our model is to produce 5 guesses. So one guess means that we provide the label, the class label, and also the bounding box of the object. So just as in the classification task, we can propose 5 class labels for an image, and our prediction is considered correct if the correct class is in these 5 guesses. So the same happens for the localization task, only that besides predicting the correct class, we also have to make sure that the corresponding bounding box has an intersection over union of at least 0.5 with the ground truth. Okay, so this is the localization task on ImageNet, and the first idea that comes to our mind is to approach the localization task as a regression task. So yeah, we have the output that are four numbers indicating the location of the box. We also have the correct output, which is the ground truth bounding box, and we can minimize this model using let's say, I don't know, L distance loss L1 or L2 and so on. So this can be approached as a regression task since we have only one object. So there is only one bounding box to predict for each image. Okay, so this is what we do for the localization. Now, if we want to do both classification and localization, then we have to change a bit this architecture. So this is the class architecture that is commonly used for classification. So it can be, I don't know, an AlexNet, VGG, GoogleNet, and so on. So it has some convolution and pooling layers. We have convolutional feature maps. So these are the activation maps from the last convolutional layer. And then we add some fully connected layers on top, and then we predict the class scores. So in order to do both classification and localization, we have to change this architecture in some way. Do you have any suggestions? So this can be a question that you can perhaps try to propose an answer. So yeah, please write down if you have any idea what we can do to this architecture in order to do both classification and localization. So right now it has only the capability to do classification of the input image. So I'm waiting for suggestions. And also after you will have a proposal, then I can also probably make a second question about the proposal. But let's first hear some ideas, some answers. So yeah, probably I'll try to keep it like this so I can see both the chat and also you can see in the same time the architecture. Perhaps you get some inspiration. Okay, so the question is, so now we have here we have a network that does classification, and we want to change this network to have the capability to do both classification and localization. So it also has to predict the bounding box for this or the objects in the input image. So the question is, how do we change this architecture in order to be able to do both localization and classification? Yes, we have the ground truth bounding boxes. So yeah, the model is supervised. So we have the class labels, the ground truth class labels, and also the ground truth bounding box location. Yeah, so maybe the question is not, I don't think is that complicated. Perhaps it's too obvious, but yeah, I just want to see if you have some intuition on how to do this. Okay, so we add the layer, but how do we add this layer? So do we put it after the classification layer, or where do we place this layer in the architecture? Okay, so yeah, we have an answer for Andrei. So the trick is we keep the fully connected layers for the classification part, and after the final conv layer, we can add another set of layers. So Andrei mentioned we can add one layer, but actually we can add the same fully connected layers as in this part, and here we just changed only the last layer in order to predict bounding box locations instead of class labels. And yeah, this is a quite easy way to do both classification and localization. So we had this classification head and this regression head that now are trained together. So the network is capable of predicting both class labels and bounding box locations. Of course, there is another question regarding where should we add this classification head. So we can add it after the final conf layer, but we can also perhaps keep these fully connected layers and then add just the last layer. So this is there isn't only one way to do it. We can do it in several ways. Okay, so for the regression head, we train the model typically using the L2 loss, which is equivalent to the mean squared error. And at test time, we can use both architectures to predict classes and bounding box locations. Another approach in this area is to use a model that predicts bounding boxes for each class of objects. So instead of just predicting 4 numbers, we modify the regression head to predict the number of classes times 4 numbers, which means that it will predict a bounding box for each possible class. So this is another option which was proposed in the literature. And another variation is where do we add this regression head, where do we do the localization. So architectures such as overfit and VGG add this regression head after the final convolutional layer, whereas frameworks such as DPose or RCNN and later models add these regression head after the last fully connected layer before the softmax classification layer. So there are variations in this regard, but the idea is quite similar. And we can also apply this architecture in order to localize multiple objects. This can be trivially done just by making sure that the network predicts the number of objects that we want to localize times the 4 numbers for the bounding box. So we have 1 bounding box per object, and we have here k objects. The only limitation here is that the network will be restricted to predict exactly k object detections, so it is not applicable to more generic images where we don't know the number of objects in the image. Okay, so yeah, this is one idea of how do we try to use this framework in order to detect multiple objects. So it can be done with this classification plus localization framework. The only problem is we can only localize a fixed number of objects. And another idea is to use a sliding window. So this approach was actually proposed before when people used a handcrafted model in computer vision. So the idea of a sliding window is to run the classification and regression network at multiple locations on a high resolution image, and for each location we predict the class and the location for the class, for the object in the respective class. And this can be achieved if it's not if the model is not computationally heavy. And we will see that with the basic framework, it is very time consuming, but we can improve this idea by converting the fully connected layers into convolutional layers. Helps us to make a more efficient computation. And then we can also combine the classifiers and the regressors and the regressor at different scales for the final prediction. And this can actually be done using implicitly using object proposals at different scales. So more on this later. Okay, so this simple idea with a sliding window was used in this overfit framework. So the idea here was to so this was the winner of the ImageNet localization challenge in 2013. So they used a convolutional neural network, and they applied two heads, one for the classification and one for the localization of objects. And here they used the Euclidean laws. So they measured the Euclidean distance between a predicted bounding box and the correct bounding box location. And the idea works something like this. So for the input image, they actually apply a sliding window using only a 2x2 grid. So they apply the network in only a few locations. So they apply it, for example, on this input image. And here they predict the class label as well as the bounding box. And they also or allow the network to predict the bounding box even if it is outside the input image. So even if the network sees this part of the cat, it can predict the bounding box that looks something like that. And then they slide it to the next input image, and then they have another prediction, and so on. So for each location, they get a class label and the bounding box. And we have all these 4 bounding boxes that are predicted for the cat. And now they can merge these boxes and classification scores in order to obtain their final prediction. So this is how it looks on images with multiple scales. And if you sample these windows over the object and look at the score maps, you kind of see this heat map over the object. So yeah, in the end, they are able to make to propose these bounding boxes that are quite good. Okay, so this was their first proposal, and in order to be able to do efficient sliding window, we need to modify the fully connected layers into convolutional layers, but without changing the operations. So the idea here is we have these activation maps that have, so here we have 1024 activation maps, and each activation map has 5x5 components. So in order here to simulate a fully connected layers with 4096 units, what a fully connected layer here does, so it connects this unit with the entire feature map. So in order to have connections to the entire feature map, we have to propose a certain configuration for the convolutional layer. So my question to you now is, can you figure out so what is the actual size of or how do we apply convolution here in order to simulate a fully connected layer? Do you have any suggestion for that? So maybe, yeah, just try to rephrase the question more concretely. So what would be the size of a convolutional filter, and how many filters we need for this layer in order to simulate a fully connected layer with convolutions? So yeah, the question is what parameters we need for the convolutional layer in order to simulate a fully connected layer here. So let's hear some suggestions. Yeah, Andrei's answer is not correct. So you're close, but that's not the right answer. Okay, so maybe just to give you a hint, so the number of filters is correct, but the size of the filter is not correct. Okay, so maybe I'll stay one more minute and I can give you the answer. Okay, so we have a good answer from Georgian. So indeed, so we have here, so imagine here you have a unit, and this unit needs to be connected to all these feature maps. So the spatial size of the filters is 5 by 5, and actually there will have here only one filter, so it has the spatial size 5 by 5. And recall that in the convolutional layer, filters span the entire depth of the input tensor. So it means that the filter is actually equal to the size of the feature maps. So here we will have one filter that applies the convolution on the entire feature map only once, and we have the corresponding output here. Then we have another filter that has the same size, and so on. So in this way we can simulate these fully connected layers. And for these two layers we can also simulate fully full connections using one by one convolutions. So this is because the activation map here is 4096 times 1 times 1. So in order to apply convolution on the entire components, the filters have to be of size 1 by 1. This is the spatial dimension, and the filters will span the entire size of the input activation map, which is 4096. So if we want here to obtain this activation map, we will have to use a convolutional layer with 1024 filters. Okay, so we can using this procedure. So mainly what we do is we apply the filters on the entire. So we make sure that the size of the filters is equal to the size of the input activation maps, and the number of filters is equal to the number of units in the fully connected layer. So with these changes, we can replace the fully connected layers with convolutions. So what's the benefit of doing this? Why do we need convolutions? So the main advantage is when we transform this architecture into a fully convolutional architecture, we can apply the model on images of various sizes. So this means, for example, that at training time we can take images just as before. So as in this example here, so the input image is only a part of the original image. So we train the model with these smaller input images, and this is just an example of architecture. So what happens if we apply a 5 by 5 convolution here? We obtain this activation map, and then we apply 2 by 2 pooling. So we reduce the size of the activation map to 5 by 5, and then we have fully connected layers that are simulated through convolutions. So here, in order to have one unit with full connections, we just have to apply this 5 by 5 filter. So it has when we apply the convolution, it has full connections to this unit here, and so on. So we can apply then at test time, we can apply this architecture on the entire image only once. So we do not have to apply it several times on the image. So essentially at test time, we do not need to apply the sliding window algorithm. We just apply, we take the entire image, we provide it as input to the network, and then we can obtain something like this. So the input image here, let's say it's has 2 extra pixels. When we apply the 5 by 5 convolution, we will have activation maps that are 12 by 12 pixels. When we apply the pooling, we will have activation maps that are 6 by 6 pixels. And now when we apply the convolutional layer that simulates the fully connected layer, here we will obtain activation maps that are 2 by 2. So this is because the 5 by 5 filter is applied in 2 locations on both axes. So what happens here is, by the end of the architecture where we obtain the output, so the output will contain the class label for the input image here, and actually here we will have 4 class labels, each corresponding to 4 locations in the input image. So we'll have a class label for each of these locations. So actually what we have done here, instead of applying the network 4 times on each sub-image, we apply it only once, and we can directly obtain the 4 class predictions. Okay, so the main advantage doing this way instead of applying the network 4 times is that some of these images have an overlap. So this part of the image has an overlap with this image, and so on. So the main advantage for the overlapping parts, the network is applied only once here instead of 4 times. So of course there is an efficiency improvement, and if the overlap is even higher between images, then there is a significant improvement in terms of time when we apply the network like this. Okay, so this is a nice trick. If we replace the fully connected layers with convolutional layers, then we can apply this architecture on larger images and skip the sliding window algorithm at test time. Okay, so this is a recap and of the results on the ImageNet localization challenge. So this is the top 5 error. So in 2012, AlexNet had the top 5 error of 34%, and by 2015 it was reduced to lower than 10%. So here the error is a bit higher than in the classification task, because we also have to predict the correct location of the object. So we have to predict the correct class, and also the location has to overlap with the ground truth. So here the error is naturally a bit higher than just doing classification. Okay, so so far for the localization of objects. So now I think we're ready to move to the more challenging task, which is object detection. So here the number of objects in the image is not bounded, so we can have any number of objects. So assuming that we have this input image, we have 4 objects, 2 cats, a dog, and a rubber duck. So we will need to predict for this image 16 numbers. And for this image we have only 2 objects, and we have to predict only 8 numbers. So trying to approach detection as a regression is not really straightforward, since the output has a variable dimension. So for an image with many objects, yeah, we need to be able to predict any number of bounding boxes. Okay, so maybe detection as regression is not really the way to do it. The alternative approach, so yeah, this refers to the canonical supervised learning problems, regression and detection. So we have to approach the task as one or the other. So now we're trying what happens to see what happens if we approach detection as a classification task. So this could work perhaps something like this. So we take a window, we apply it on the image, and we try to classify the window with the corresponding object class, and we slide the window over the image, and when we detect an object, we expect the classifier to work correctly. Okay, so this is basically the sliding window approach. The problem is that we need to test many positions and scales. So with deep neural networks, this is not very cost effective. But in general, if you have I don't know, a fast enough classifier, you can just try this approach. It should work fine. And actually it was used, for example, to detect people in images with handcrafted models, such as the histogram of oriented gradients plus SVM. So yeah, in this approach, to detect people in images, we take an image pyramid. So we have the original input image, we have we take the image at different resolutions, we extract the Hog feature pyramid, which is the Hog features corresponding to each image level, and then we apply a sliding window on top of this Hog feature pyramid in order to detect people. So this approach works because SVM is a linear classifier and can be efficiently computed on top of the image, and also these hog features can be extracted from the entire input image once, and we actually can apply the sliding window on top of the hog feature map instead of the original images. Yeah, and as I said before, this approach is not really easy to do with convolutional neural networks. So the alternative way to do it is just to look at a tiny subset of possible positions. So the idea is just try to figure out some probable locations of objects in images, and we apply our framework only for these subset of locations. And this idea was explored previously in literature. So the task is called region proposals. So to propose regions that may contain objects. So in this task, there are various approaches in which people try to find like these blobby image regions that are likely to contain objects. And the approach is typically class agnostic, so it's just trying to detect something that looks like an object, but it doesn't know the class of the object. It's just more maybe a region that is also not very refined. Maybe the contour of the object is not really well identified by this approach. The main idea is that it works pretty fast. So for example, it can also detect these flowers which may not be of interest to us, but since they look like some blobby objects, they will be considered as potential regions that contain objects. So these are region proposals. One approach to do this is to use bottom-up segmentation. So we can use a low-level segmentation approach, like something that generates super pixels, and then we can merge these regions into at various scales, and for each scale we can transform these regions into potential bounding boxes. So then we will apply our CNN model on top of these bounding box proposals in order to estimate the class and the bounding box location. So this approach based on segmentation is called selective search. So it was introduced before deep learning models in order to speed up detection of objects in images. And the paper is called selective search for object recognition. And there are many approaches in literature that do region proposal, and they are based on various methods. And these are studied in this PAMI paper in 2015, and that is also trying to rank them with respect to repeatability, recall of the detected objects, and so on. And it seems here that they also awarded stars for each of these approaches. And based on this study, the RCNN model opted to use edge boxes, which is also efficient in terms of time. So among the compared models is quite fast. It needs less than 1 second to produce object proposals, and it also scores very well in terms of detection and recall. So yeah, they opted for this approach, and then the idea was simply put together. So just as we tried to explain so far, so we apply these edge boxes in order to obtain object proposals. So we have these bounding boxes. For each region, for each proposed region, we apply a convolutional neural network that has a classification head and a regression head for the bounding box of the object. And here for the convolutional network is actually pre-trained on ImageNet, and these SVMs and regression layers are fine-tuned for the object detection task. Okay, so this was proposed at CVPR 2014, and the paper is called Rich Feature Hierarchies for Accurate Object Detection and Segmentation. So in the training of the RCNN model, so RCNN stands for Region-Based Convolutional Neural Network. In the first step, they trained the classification model on ImageNet, or they just use a pre-trained model. So the CNN model depicted here is a pre-trained model. Then they fine-tune the model for detection. So in order to fine-tune the model, they remove the 1000 ImageNet classes, and they replace them with 20 object classes in Pascal VOC. So these experiments were done on Pascal VOC. So they also add one class for background. So in total, their model was trained with 21 classes, and they removed of course the final fully connected layer, which was replaced with this model that had only 21 units instead of 1000. Okay, and they also extract region proposals using edge boxes, the method that I explained earlier. And for each region in the image, they apply the CNN. So they pass the region through the CNN, and they take the features from the last pooling layer. So the last convolutional layer also is followed by a pooling layer. So they use those features before the first fully connected layer to be used for the classification and regression layers, which are trained. Okay, so for each object class, they train a binary SVM. So these will classify regions. So we have the object proposals here. These are labeled with specific class labels, and then the SVM is trained on top of them. So yeah, for the dog class, we have a different labeling and so on. So the labels can be obtained from the ground truth annotations. And okay, so this is for the classification part. They train binary SVMs for each class. And the last step is also to train the bounding box regression. So for each class, they train a linear regression model to map the pooling features to the ground truth bounding boxes. And this can also make up from slightly wrong proposals. So even if the proposal is not perfectly centered on the image, since they have this regression incorporated in the model, they can try to predict the correct bounding box for the object. So even if the object is not centered or is truncated from the region proposal, they can correct this through the bounding box regression head. Okay, so we will present results on Pascal VOC on the ImageNet detection challenge, which was introduced in 2014, and also the Microsoft Objects in Context dataset, or MS-COCO. So here we have 20, 200 or 80 object categories, and the average number of objects. So in Pascal VOC we have 2.4, in ImageNet. So since ImageNet was usually was collected to have only one instance, one object per image, the average object per image is 1.1, so there are only a few images with more than one object, while MS Coco has an average of 7 objects per image. And for the evaluation, we use the mean average precision. So the mean average precision is based on computing the average precision for each object class. So recall that the average precision is a curve metric, and we for this curve metric we measure a detection as true positive if the intersection of a union with respect to the ground truth bounding box is greater than 0.5. So this is typically written for short as MAP at 0.5 or at IOU higher or equal to 0.5. So this is the short notation for this this metric. Okay, so mainly the higher the average precision for a class, the better the model, and of course this is also reflected in the mean average precision. Okay, so we have these results with the RCNN model that we presented. So RCNN improves the results from previous approaches based on deformable parts models or region-lets. So these are handcrafted models. RCNN is based here on AlexNet architecture, but without the bounding box regression head. If you add the bounding box regression, you get some improvements, and we can obtain further improvements by using deeper models. So essentially, yeah, in just a couple of years, using this approach, they managed to almost double the performance, the MAP with respect to deformable parts model. So here it's 33%, and here it's almost double, 66%. Yeah, so the first big improvement was seen by adding the deep neural networks. Then also the bounding box regression seems to help a bit, and using even deeper networks brings a good improvement. Okay, so the results in terms of accuracy are quite nice, but there are also some problems with the RCNN model. So one problem is that it is very slow at test time. This is because we need to run the network for each region proposal, and for one image we can have hundreds of region proposals, so it becomes slow at test time. And also the architecture is not trained in an end-to-end fashion, so the SVMs and the bounding box regressions are trained independently, so the CNN features are not updated in response to the training of the SVM and the regressors, and this is suboptimal. So we can expect better results if we are able to train this framework jointly. Okay, and also the pipeline is quite complex. So we have the region proposal component, we have the pre-trained neural networks, and we also have the SVMs and the bounding box regressors that are trained independently. So the RCNN authors tried to propose this improved model in 2015, and this model is called fast RCNN. So The main update was to following the same idea using used in overfit. They apply the convolutional layers on the entire image only once. So instead of applying the CNN for the entire for each region proposal, now they apply it only once for the entire input image, and this produces a larger activation map. And on this activation map, they project the region proposals on the activation maps. So they still apply the same region proposal approach that is independent of the neural architecture. And the region proposals are projected on the activation maps. So this means that, I don't know, if here we have a large bounding box that corresponds to this region, well, it will correspond perhaps to a bounding box in the same location. We have to rescale the region proposal with respect to the size of the activation map. Okay, so yeah, we project the region proposals here, and then we apply the last part of the network, the fully connected layers, on top of these region proposals. So they didn't thought about changing the fully connected layers into convolutional layers. They just said, okay, we can pass the whole image through the convolutional part. We project the region proposals on the activation maps, and then we apply the last part, the fully connected layers, on each region proposal. And they also integrated this into the architecture. So here, in order to integrate it, they had to introduce a new layer, which is called the ROI pooling layer. So what this layer does, it extracts some fixed size feature representations for each region proposal, and these are passed to the fully connected layers, which have a softmax classifier and the bounding box regressor that are trained end-to-end through this pipeline. Okay, so they try to solve the first RCNN problem, that is slow at test time, by introducing this CNN by applying it only once on the entire input image. The second problem, the fact that the training is not end-to-end. So since they integrated this model, they can now backpropagate the error through the entire model. They reduced the complexity of the training pipeline. They still have an independent region proposal model and this CNN architecture. So it's simpler than the RCNN architecture. And yeah, they also managed to train the model end-to-end using backpropagation. So now one of the ideas that they the main novelty perhaps is this region of interest pooling layer. So how does this method work? So assuming that we have this input image and this object proposal, we in order to obtain the fixed size features for the fully connected layers, we have first to, so once we project the region proposal on the activation maps, this can have, I don't know, if the proposal is larger, we'll have more features. If the proposal is smaller, we will have less features. So we will try to reduce this tensor that corresponds to the region proposal using an approach. So we divide it into a grid of the desired height and width. So we assume here that h and w is are higher than lowercase h and w. So assuming that, let's say, these are I don't know, twice as lower, then we just we can divide this region into 2 by 2 and just take the max over each resulting region. So they actually apply MaxPooling on this region proposal that is projected on the activation maps here, and they obtain this fixed size feature that is so the number of channels is the same, that only the size is reduced from capital H and W to small h and W. And this also allows backpropagation. So this is, since it is based on MaxPooling, it can the model can backpropagate just as in using a standard MaxPooling layer. So here is another example on how the region proposal works. So assume that we want to have here small h and small w are 2. So we want to obtain feature maps that are C times 2 times 2, and this is the this is an activation map from this convolutional layer. So it is just one slice from this cube. So here, suppose that we have this region proposal. So this is the region proposal projected on the activation map. So here we divide it into 2 by 2 components, and then we take the maximum from each region. So this can be applied even if this region cannot be exactly divided into 2 by 2. They can just choose, for example, to use 3 components for this part and 4 for this part, and so on. Okay, so this is how the region of interest pooling layer works. And the goal of integrating the region of interest pooling layer here is just to make sure that these features have a fixed size, and now these can be used. So we actually obtain here, for each region proposal, we will obtain a tensor of features that look like this, and for each tensor we apply the fully connected layers on top in order to propose a bounding box and to estimate or to predict the correct object class. Okay, so now they have some interesting comparison in their paper on Pascal VOC. So the training time is about 9 times faster for fast RCNN compared to RCNN. And also the test time, so for RCNN it takes about 50 seconds per image, which is quite a lot, and for fast RCNN it's about 0.3 seconds per image. But actually here they do not so this is the speed up of the framework without including the region proposal. So when you add in the region proposal, actually you add 2 or 3 seconds to both models, as you will see in the next slide. So for faster RCNN, as I said, yeah, the test time doesn't include the region proposal. So actually when you add in the region proposal, the time is about 2 seconds here, and here we have about 50 seconds. So the actual improvement is about 20 times instead of 146 times. Okay, so still this 2 seconds per image is reasonable, but it's not applicable on I don't know, if you want to do real-time object detection, you cannot apply this framework. Okay, so in their latest development was okay, so this region proposal really takes a lot of time. What if we try to include it in the framework and try to train it end to end? So in um, in 2015 for NIPS, they proposed faster RCNN, which with respect to fast RCNN, it is just so it's the same architecture. The only change is just adding the region proposal model into the entire framework. So here they replaced the handcrafted region proposal approach with a region proposal network. So this is added. So here we have the feature maps as before, and instead of having some region proposals to project on these activation maps, we have here now the region proposal network, which produces the proposal. So this is applied directly on the activation maps, and with the proposals from the region proposal network, we can now have the same input as before. So we have the activation maps with region proposals, and these go into the region of interest pooling layer, and the rest of the architecture is identical. Okay, so this region proposal network is really a lightweight network that can predict object proposals. So in the region proposal network, they apply this sliding window over the convolutional feature maps, and they really here the sliding window is actually simulated through a convolutional layer that uses only one convolutional filter. So this is applied on top of the convolutional feature maps, and then they have a pretty lightweight architecture that has to predict classification scores. So this is a binary classifier that estimates if this window is containing an object or not. And then they also have a regressor for the bounding box location. So this provides the object proposals. So it's actually as a small network that does detection, but it's not able to classify the objects into classes. It's just proposing locations for objects. So in order to propose a variety of region, they use a number of anchor boxes. So these are predefined boxes. So for each location in the image, they actually apply various convolutional filters that have various sizes. So these are simulate these anchor boxes, and these are translation invariant. So we have the same anchor boxes in each location of the image. And yeah, this is how they obtain the region proposals. So in the original paper, when they introduced faster RCNN, they used alternating optimization. So they trained the CNN and the region proposal network independently. But since the publication, they actually now the framework is trained in an end-to-end fashion. So there is actually only one network that is optimized using 4 joint losses. So we have the loss for the region proposal classification. So this actually classifies each anchor into object or non-object. We also have the region proposal regression, which provides the proposal for locations. And then we have for the faster RCNN model, we have the classification head and the regression head. Okay, so this is the summary of the faster RCNN architecture, and now they really managed to reduce the time to 0.2 seconds for faster RCNN. So these times are reported with object proposals. So here you can see that actually the speed up with respect to faster RCNN is about 10 times, and with respect to RCNN is about 250 times. So this is a much faster object detector. The performance is slightly better than RCNN because these two are trained in an end-to-end fashion. And still, this is considered a bit slow, and there are even faster object detectors such as YOLO. So we are also going to briefly discuss a bit about the YOLO object detector. Let me just see. Yeah, so I think now I answered the question of Mihai. Now I saw the question. So actually, yeah, we didn't lose performance between RCNN and fast RCNN. We actually gained a little performance because of the end-to-end training and co-adaptation of the CNN architecture with respect to the output. Okay, so now for the COCO dataset, the state-of-the-art, or I think now recently faster RCNN was surpassed by deeper and slower architecture. So really, if you want to improve performance, there isn't a more efficient architecture. So the faster RCNN has an MAP of almost 60% for the intersection over union at 0.5, and for intersection over union between 0.5 and 95, it's lower. So okay, so these are the results for ImageNet detection between 2013 and 2015. So in 2015 the state of the art was attained by this ResNet ensemble. So the original faster RCNN as a single model produces this output, and when we use ensemble models we can improve the results. This is when we also combined the model with ResNet. So when you change the backbone architecture from VGD to ResNet, you can obtain improved results. And if you add an ensemble on top of this, you can further improve the results and go over 60%. Okay, so now we also have a few slides about this object detector YOLO. So this was introduced at CVPR 2016, and I was actually there at the conference when it was presented, and the people were really impressed by how fast this object detector worked. And actually Joseph Renbon was doing a live demo on scene from his laptop, and the algorithm, I remember it was running in real time on the laptop. So he was recognizing some objects, some toys that he brought with himself. So it was really nice to see that it works so well in this live demo. So here the idea was just a bit simpler than faster RCNN. So in faster RCNN we have this region proposal network that kind of does the first rough estimation of the object proposals, and then these object proposals are further refined through the ROI pooling layer and the rest of the architecture. And in YOLO, you just approach detection as regression, so it's a more straightforward application. But in order to be able to localize and to detect any number of objects, the idea is to divide the image into a grid, and for each grid we have a fixed number of bounding boxes and coordinates. So the idea is that we have these predefined object proposals. So for each cell we have a set of predefined object proposals, and from these we apply the framework and try to estimate the output. And of course, these predefined object proposals can also be estimated on a training set. So we can, for example, learn the object proposals prior to training, but once they are trained, these remain fixed. So there is no component at test time that tries to propose to make any proposals. These are fixed at test time, and this makes the architecture much faster. And yeah, the results are quite close to faster RCNN. So here you see some results with faster RCNN on, I think these are on Pascal VOC, and you can get results like, yeah, this is Pascal VOC. So you get like 73% or 70% MAP, and with YOLO you can reach about 63%. Yeah, so this architecture, so you can see that here you can really obtain the time is about 3 times as fast as faster RCNN, or actually of this version of faster RCNN. So if you look at the original faster RCNN, I think it is this architecture. So you can, yeah, it's about 0.2 seconds, so it runs at about 7 frames per second, where YOLO runs at about 45 frames per second. So yeah, it's about 6 to 7 times faster compared to faster RCNN. So it is much faster, and of course the MAP is not as good as faster RCNN, but it's quite close. Okay, so I think this is the last slide. So just a short recap of for today, and we have enough time. I also want to maybe to discuss a bit about the Kaggle competitions. So I'm going to, just before the recap, you can write down questions about the lectures, and also questions about the competition. I'm just trying to save a bit of the time and from the transmission delay, but okay, let's do the recap. So for localization, this is applied when we have a fixed number of objects. The common application is when we have only one object per image. In order to obtain the bounding boxes, we apply regression using the L2 loss. It is much more simpler than object detection. So if you have this localization task in any of your projects at work, on personal projects and so on, and if you want to do localization, really you have to think about, do I really need to do detection? So I need to detect multiple objects, or if I just need to detect only one instance, perhaps it is easier just to apply this localization framework that is based on adding a regression head with L2 loss. Okay, so we also saw this efficiency improvement from overfit, where the fully connected layers are replaced with convolutional layers. And this is a nice idea that can also be applied in other domains where you want to, instead of applying the CNN several times over the image, you just apply it only once and you get a slightly larger output that you can further process. So the idea of replacing the fully connected layers with convolutional layers allows you to use images of various input size. But you also have to manage what you do with the output. So if you provide a larger input image, then you will have several outputs and you have to do something with the output afterwards. Okay, and recap for object detection. So we mainly focused on the faster RCNN model, which builds on top of the previous versions, fast RCNN and RCNN. Okay, so yeah, this sums up the lecture for today. So let's see if there are any questions here. It's not clear what this question is related to, but yes, the AUC is area under the curve. Was there AUC anywhere in the slides here, or no? So maybe yeah, not clear what the question is about. Okay, so a few words about the challenges. So I needed a few extra days to generate the datasets and to prepare the challenges for you, but as of yesterday, you have both challenges online, so you can start. I see that there are already a few that started to look at the computer vision challenge, in which you have to classify images generated by deep networks into 8 classes of objects. So we tried to generate not so many images, so we try to control the data set so it doesn't have a very large set of images. You have about 30,000 images for training, and also the images are not that large, they are just 32 by 32 pixels. So you can approach this task with a deep model that is trained even on CPU. It may take several minutes or hours, but that's manageable, I think. So since you do only 2 submissions per day, I think you have enough time to train two models per day and to make a submission if you really want to benefit from all the available submissions to the competition. Okay, so just bear in mind, I think maybe one thing that is not written down here is that you have to propose a deep learning approach. So since this is a deep learning lecture and labs, you cannot propose shallow approaches, or I don't know, like Sift or Hog and the bag of visual words and so on. So you must train a deep network for this task as well as for the other task. Okay, so yeah, if I think in order to join you need to click this button here. So you have to go to the rules and accept the terms and conditions. So here it is, you see the rules. You can make submissions until the 3rd of January next year. And after the submission deadline, you can also have a few days until the 7th of January to prepare your documentation of the project, which must be submitted to your lab supervisor. So here you have some ideas of what you can include in your report. So you have to describe your architecture, any details about training, data augmentation, and so on, and also present results like accuracy and confusion matrices on the validation set. Okay, and also perhaps another slight change here. So initially I was thinking to use only the full grade, to give a full grade only for the first 5 competitors, but I increased this to 10 competitors here, so we have 50 places in the ranking for grades higher than 5, and the same happens for the other challenge. Yeah, I don't know. So as you know from the last year, I'm not a fan of copy pasting code from the web. So you must try to design your own neural architecture and try to train it by yourself and so on. So even if you use advices from tutorials or from the internet, you really have to write down your own code and not just copy paste code from some tutorials. So yeah, you're not allowed to use code from online, and also you're not allowed to share code with the other participants, either privately or publicly. So posting code on GitHub is also not permitted. Okay, so yeah, so this was the first task, and the other task is could be maybe a bit more challenging because the data is not as we don't have as many examples. So here we have about we have 10 classes with a few hundred examples per class. So there are about more than 2,000 training examples and more than 1,000 test examples, and you also have a small validation set to tune your models. So yeah, this is based on the Romanian language. So you can use here, I don't know, additional data if you want to train models for word embeddings and so on, or if you want to use pre-trained models, that's also allowed. Once again, one important aspect here is to remember this is you're also required to use a deep learning approach. So using, I don't know, bag of words and SVM is not permitted in the competition. So even if you use it, you will be disqualified. So please use deep learning approaches. Once again, I think the data set is could be a bit challenging because there aren't many examples, but you can definitely train deep learning approaches, so the data set is not so large, and the rules are about the same. In order to participate here, you have to accept the rules. So really, I don't think there is any change in the rules actually. Yeah, the rules are actually identical. Yeah, the only difference is that the competition started only 1 day later, so it's not such a big deal. So the deadline is the same, 3rd of January, and for submitting the documentation is 7th of January. So just bear in mind that you do not have to participate in both. It's enough if you participate in only one of the two competitions. It's really if you have more time to dedicate for the projects, you can try both competitions, and perhaps you will your first guess might be better if you look at the leaderboard, and then perhaps you can opt for that challenge. I don't know. Okay, so going back here to see if there are any questions. What is the MAP metric? Okay, so maybe doing a quick recap from the practical machine learning, but just let me see if there are any other questions. Yeah, so AP is similar to the AUC. Yeah, now I see the full thread. So your question is about what is the MAP metric. So as I said, it's the mean average precision. So it's similar to AUC, it's only based on a different curve. And the mean, so the average precision is for one class and the mean for all object classes. So it's just computing the average of all the average precisions. And this average is called the mean average precision. Yeah, in order to close this, maybe I'll not start from the beginning. I'll try to, this doesn't work right. Need to close this perhaps. And now I can open this and going to performance metrics. Waiting for the slides to update. This is not working. Let me retry. Okay. Okay, why aren't the slides showing up? This is weird. This never happened before. I'll try to quit this as well. Okay, maybe there is a problem with the slides. Yep, something is wrong with the slides, I think. I cannot go out the full screen. Yeah, welcome to PowerPoint. It's crazy that people think that Bill Gates can engineer a vaccine to insert chips when PowerPoint works like this. Okay, so yeah, I was trying to maybe to show you some slides for the, maybe if you have the slides from last year, you have yeah, you have the AP there. Okay, so yeah, it's the question, what is a good score for the test in both challenges? The best you can get, I don't know. Yeah, I don't know what's a good score, so you can try and see. I only tried some baseline models to make sure that you can make some predictions, but I didn't try to obtain the best possible performance for the models. So yeah, I don't know. So I cannot give you an answer. So I don't have. Maybe you can. I'm sure you can actually obtain better results than the baselines that I tried out. Can we extend the deadline for at least one competition for a week or two? No. Okay, so the private test data is already provided, so it's just that. So I gave you a test set. So yeah, test set is in this document, and for the other competition you already have the test images. It's just that the leaderboard here is computed only on 20% of the data set. So it means that if you have 5,000 test images, you see here the ranking only on for 1,000 images, and after the competition deadline you will also see the ranking for the other 4,000 images. So this is automatically computed on Kaggle, so you don't have to do anything about it. Just make sure in the end, sorry, wrong window, just to make sure in the end that you predict the right sorry, you choose the right models that you want to submit. So yeah, this is also written in the rules. So in the end you will be ranked considering 2 models. So if you make more than 2 submissions, the system will automatically select those that obtain the best results on the public leaderboard. But if you want to make a different selection, you have to make your selection before the deadline. The 20% of the data is randomly chosen, but it's the same for everyone. So it's chosen randomly by the Kaggle platform, but it's chosen only once for everybody. So the ranking is comparable. Yeah, so your model must contain some deep neural network. So if you want to use also shallow models, that's possible, I think, but it's not perhaps. So when we also look on your project, it's really maybe if you use it just to gain maybe 1 or 2%, that's okay. But if it's like the main idea of your project, to use some shallow approach and then just use this deep model for something that is not relevant, you will be disqualified. So perhaps it would be better just to use deep models, just to not to be confusing, or not to have a discussion. So I prefer just to stick to deep learning models, to not to give you ideas. Yeah, I don't know, but if you, for example, you can, let's say for the text classification task, I suppose you can extract some bag of words, let's say, and then you apply some deep approach on top of that. That's of course possible. I mean, if you do a model that's end-to-end, and it doesn't include anything that is deep, that's not acceptable. Yes, I think I already answered this question last time. So you can do transfer learning, you can use pre-trained models, whatever. Okay guys, so I think we got a nice question and answering session. I'm going to end the stream here and see you next week. Okay.